Recording in progress. Hi. You know the deal. And thing. Paper. You already know what's going on. We got paint. We got smiley face. We got Orchestrate by Yeet. Yeet is my favorite rapper of all time. I know probably every single Yeet song you ask me, I know it. Um, and today we're going to be doing Lab 5. We're going to be doing all Lab 5. Fair warning. I'm going to show you guys, get zoom out of my face. I should probably share my screen. Where I say, let me show you guys. I literally drew a smiley face you guys didn't see. Oh shoot, you guys didn't see my smiley face, guys. Well, I was playing Yeet, bro. I put a little, he's like a little face. It's like a Neon Abyss type thing if you've ever played that game. It's a valid game. All right. So the finished code, basically the bit is that I give you like a little blueprint, a little footprint, but like some of the stuff like the tab instruction, just not implemented. The and instruction, not implemented. Uh, not implemented. I don't know why this is commented. Maybe there's a syntax error that I'm not seeing. That should be good. Uh, you know, I'll even just what? What is? Oh, oh my God! Yeah, there we go. Or so you guys can see, like I left some stuff undone. Adding. I did two of them, and we'll walk through doing two of them. Those will be the load instruction and the two's complement instruction. I'll show you all that now. Guess. Let me stare at my soul a little bit so I can make sure you guys can see. I can see. So I'll show you guys a little bit what we're making. We're making this. This looks familiar, doesn't it? Uh, A, B, ALU output, input bus. But this time the input bus is bigger. Look at that. We can input the number 8. We can actually input all the numbers between 1, 2, 3, 4, 5, 6, 7, 8, all the way up to F. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, B is 11, C, D, E, F, 12, 13, 14, 15. All right, it's hexadecimal. Hopefully you know that. Um, why do this? Hopefully when you demo your Lab 4 to a Pi, you realize that it's a pain in the ass, pardon my finest French, for to use. Cell A, cell B, this, that, the other. We don't think like that. Computers think like that, right? It's a lot easier to say, do this, do that, and have it kind of handle the little in between. If you write in a programming language, this is exactly what you're doing. When you say if x equals 2, you don't really care about how it's making this comparison, whether it's actually doing like a bit by bit comparison, or maybe it's doing x minus 2 and checking if that's equal to 0, or maybe it's, starting two timers, and if they like if X delays 8 seconds and two delays 2 seconds because X is 8 and two is two, right? If two overflows first, yeah, it doesn't, we don't care. We just want to know if they're equal, right? And so we don't care about how to do two's complement. We don't care about how to load. We just want it to happen. And so with this guy, you'll be able to encode an instruction. That's these three. So the current instruction is going to be 000. That's load the input bus. Okay, you'll be able to encode the destination. We have B and A, B and A. I think the lab document says that this is A and this is B. I couldn't care less. You guys know how to, you'll know in the code where I put 0, you'll put 1, or you can just be kind of wrong to you. So we've got the instructions, we've got the destination, we've got the start flag, we've got literally nothing. There's nothing on this switch, and we have the input bus, right? So as a testament to how simple this is, in Lab 4, we were out, completely out of switches, and we wanted to put more on the input bus and we couldn't. Now, we literally have a free switch. What? How cool is that, right? So we've got a reset on the button, a clock on the button. Notice pressing the clock does nothing. Okay, why is that? That's because let's say we're in 000 instruction. A will be our destination, so this guy here. And we're going to load 8, the number 8. Okay, I'm going to start clicking. I believe the clock is the top guy. Nothing happens. Maybe I'm clicking the reset. Nope, that's not it either. So what's happening with the start bit, this bit right here, has to be true for instruction to start. So boom, you can see we have like a instruction is running indicator, and the instruction runs. We load 8 into A, and the instruction is running indicator turns off. Now this is really done, but this LED is active low. So it's showing it shows when I can't speak English. The LED is on when done is false or when done is zero. And so if it's not done, it's running, right? So the LED is really a running indicator, but you could also say it's a done indicator that's active low, whatever, right? You get the point. No LED, no instruction. No LED, no instruction. We're in idle mode. Okay. Let's say I now want to load something into B. Boom. Start bit still true. I want to load uh, 4 into B. We're decoding the instruction. That was one clock cycle. We loaded 4. That's another clock cycle. Okay. I'm going to turn the start bit off. Okay, start is now false. Spam. Nothing happens. Reset. Switch it all back. So that's what we're building today. Hope you're excited. Here's a little functional block diagram. You'll also see this in the lab document. You got the idle state, which has some like combo logic that goes to other states, and those states all return to idle. So it's like we're idling. We picked an instruction, we run the instruction. So when I click the button, you saw the light would come on, and I click it again and something would happen. That's this loop. Pick an instruction, that was one press, run the instruction, that's another press. And some instructions will take 2 of these or 3 of these. The graduate college button, it actually, instead of states, it has pits of hell. There's 9 of them that you go through, and I'm on the bottom one. I also have a little cheat sheet. Cool. Um, so I'm making this video because a lot of you guys used, learned from, or copied, shame on you, my design for Lab 4. And I feel like even if you understood it, it's still like riding someone else's bike. I'd like to show you guys how to get started with my design. And so what am I going to do? I'm going to open up Notepad, and I'm going to do the thing that makes me the most angry, and that is take all of my code and delete it. So this will be Ctrl. All right. Um, this guy, actually, I don't really need to save him, but I have a billion bytes of RAM. Who cares? This is the RALU registered ALU. And this is our final. Notice I called it Lab 4 because I started from Lab 4. Okay, I opened Lab 4 and started working. You don't need to make a new project. Don't do that. Make yourself miserable. Lab 4, I'll call this video. Okay. So first, I'm going to make it look like it did when you guys turned Lab 4 in, which means I'm going to delete all the code in RALU. Ugh, I hate doing that. I'm going to delete all the code in controller, and I'm going to delete all the code in Lab 4, but that's not how it'll look for you guys. Uh, it'll probably look something like this. This is your Lab 4, right? Hopefully this checks out. Let me make sure I've made no kind of compilation errors, and we'll get into it. This is literally like the Lab 4 if you follow along, or, demoed successfully to your Pi. I've got the 7 segments, we've got the muxes, the just small bus with the 0 to tide high. And yeah, my code's compiling. It compiled. Pretty cool. I get really upset when I can't see myself, so I have to click minimize and zoom. There we go. Now I can see myself. So where to start from here? So the bit from the lab doc, the bit is that we're going to have the register data path, which is really just register data path is just this file, right? And we're going to have the controller, right? And so instead of having just the top level being the register data path, what we're going to do is we're going to have the register data path R, RD, and we're going to have C, and these are all going to be like part of a file. So RD and C are going to be like their own files. So this is going to be the register data path. This is going to be the controller, and they're all going to be part of Lab 4, which is really Lab 5, but don't chill. All right, I'm going to unplug my DE10. So I don't need it right now. I'm going to leave my headphones plugged in. Okay. So, like, what does that mean in practice? We're going to do a little file. I'm going to do file open. You're going to do file new. File open, and I called it RALU. RALU. Now I'm opening it. It's an empty file. So you just file new, and you're going to just take literally everything and copy it over. This is the exact same thing as in Lab 4. And now make sure you copied it over, and then we're going to delete everything in lab4.bhd. Okay, cool. So in RALU, a few things. Anywhere it says lab 4, rename it to Ralu. Make sure you actually do this. Ralu. That's it. Okay, a few things. Small input bus. Nope. Now it's an input bus. Okay. We remember I showed you we weren't limited, so now it's three down to zero. So we have to go down to about approximately here where we have the signal called input bus. We reduce it to ash, and we take these lines and they just disappear. And all of a sudden, boom. This is why I name my variables and signals like I do. You see how easy that was? Rename the input, delete two things. Boom, bigger input bus implemented. Okay. Hopefully you guys got that. Clock is chilling. This is all the same. This is all the same. Yeah. Trying to think if there's like anything different, but I'm struggling to believe that there is. Double check for y'all. I'm reading. Chill, chill, chill. I'm gonna go ahead and say there's like nothing different. If we get caught up on something, we get caught up on something that's chill. But boom. Okay, so that was all you needed to move your data path. You already made it, right? That's kind of the bit. If you didn't demo lab four, drop the class. I don't know. Beg your pie for a working version. So you're gonna make another file new. I called it controller. I think I spelled it wrong, but I could not care less. Controller. Let me get the notepad code open so I can look at it if I need it, but I probably won't. Okay, so this is the first code. We're gonna make this little entity controller. I'm not gotta spell it the same. Is port and make sure that's the same. It is. Okay, you guys have seen this a million times. What is the input to the controller and what is the output? So I mean some simple ones. I mean, it's gonna have a clock, and maybe I should grab my imports and actually import them before I start yapping. Boom, 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 clock in standard logic. Okay, it's gonna have a reset in standard logic. Okay, it's gonna have like a start signal. It's gonna have a done signal. It's gonna have CN, which is a CN. Okay. I'm gonna like explain something real quick, just because there's no way to not name it in a confusing manner. So I'm gonna do some explainerizing. So here the lab document does its best to confuse you by saying that this guy has CN. I'll move my head a little so I can draw. Cool. So this guy has C out, right? Ignoring this for a minute. The RALU you guys made registered ALU data path, whatever I'm gonna call it RALU from now on. The RALU you guys made has a C out. Okay. The way that this works, and I'll explain why it works this way. The C out is routed all the way around. Okay. And then the controller determines the CN. So what does this mean? What does this mean? Why am I spending time talking about this? This actually means that the CN is an output and it's a standard logic vector of zero down to zero, I think. I'm just gonna make it standard logic. There's some like shenanigans you can do. I'm not doing them. It's a standard logic. It's a bit, right? And so the reason I took some time to explain this, look at this. It's called CIN, but it's an output. It's an input to the data path. It's an output from the controller. So in controller land, it's an output, right? And similarly, C out, yes, it's called out as an output, but it's coming into the controller from the data path. So C out is an input. I know it's confusing. Deal with it. How else would you name them, right? You want four different names like Ralu C out, controller C out, or would it be CN? Does the CN come from C out? This name nomenclature, this system of naming makes it so that you pipe CN to C out, or I mean CN to CN to C out to C out. You'll see. This makes it easier. Deal with it if it confuses you. I'm sorry. It's a little abusive notation where like the names kind of come around. Inputs as outputs, outputs as inputs. Weird, but it's how it is. Okay, next we got these we got these instructions and destinations. So those are definitely inputs. No, nothing else confusing besides that, right? And everything else is what you'd expect. It's a 3-bit instruction, so and I'm gonna say dest is a is an in standard logic. Now you're gonna notice this is literally wrong. Pull up the lab doc. Says when dest is one, when there's a one, we should put into B. But I'm saying this why? Because I'm not a slave to the system. Okay, I don't care. I don't care. I don't do what the lab doc tells me to. I'm ballsy. Yeah. So if you really want, you can do dest is B and like go from there. But I don't care. I do not. So pretty sure like that's all it needs. No, I'm tripping. So it also has to like the bit is that the controller is driving the data path, right? And so, what does the data path work on? AKA, what were the switches that you used to demo for Lab 4? We had something that determined A, you had something that determined B, and you had something that determined the opcode. And those are demonstrated here, here. Really not a CN, really just this guy and this guy. So, I mean, what were those? Those were cell A is going to be an output standard logic vector, like 1 down to 0, right? And we're going to have something similar called cell B. And this is like going to flip the switches for us, if you get my meaning. And then the op code, I'm just going to call op, is 3 bits instead of 2 because we had 8 operations, 2 to 3 is 8. Right, so we had 3 bits. To jog your memory on like what these symbols like represent, remember like 1 1 meant like store B, like look at B. So if we had like cell B equal 1 1, that meant that B was going to feed B. And the opcodes had like certain means like 000 meant not A, for example, for the opcodes. So I'm gonna check my work. I'm gonna do yeah, I'm gonna check my work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Are you kidding me? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, I'm not kidding you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's chill. I got it right. I just miscounted. So, I mean, is what I wrote here surprising to you? If the answer is yes, it was probably a I don't know what I'm building, not I don't know how to build it. All right. Hopefully this kind of cleared up what we're doing. We have a controller. It shares the same clock as our CPU. Not that the CPU really uses a clock that registers do, but CPU's all combinatorial. He's got to reset like everything else in the world. We have a start signal. We have C out and C in signals. Is an instruction and destination register. Register, they're like inputs. We can select A, we can select B, and have an opcode. These are for driving really these are for driving the data path, right? Remember, this was 1, 2, 3, 4, 5, 6, 7 switches, and the other 3 switches were the input bus. All right, notice the input bus doesn't come in here. Why would it? Right, we don't need to look at the input bus. Only the CPU needs to look at the input bus, and so we'll see that that kind of works. Um, out standard logic done. Out standard logic. Cool, cool, cool. Controller. Okay, so let's write some architecture. Architecture. Behavioral of controller is begin and architecture and behavioral. And so this is a great time to, compile, make sure everything works. And I have a question for you guys while this is compiling. Can you do a little thinking in your noggin? I wonder if I can like zoom in at all with this, make it bigger. I don't like staring at the tiny screen at all. No, what about like zoom view? Word, utility windows. There we go. Maybe that's a little better. Anyways, Entity lab 4 undefined. So that's because there's no code here, but who cares, right? It's not what we're looking at. Um, so start writing this architecture. It's a little too zoomed for me. There we go. It's probably better. Okay, so but can you guess what's going to go in here? This is important. We've been doing this all semester. I'm going to double check because if I get it wrong, I'll be very angry with myself. I guess we can do that first and get on to that. Okay. Anyways, the answer to your question is a process block and a case statement. If you're surprised, what have you been doing the whole semester? Every single part we've wanted. Process block, case statement, process block, case statement. It's tried and true. Before we do that, a few things. First, we mentioned this is a state machine. If you guys did lab 3, you remember that there was a special way, which I don't remember the syntax for, so I'm not going to type it out, to define custom states. And that was this, right? Zoom out a little bit. All right, we have a type called possible states, and we are either idling, we have the load instruction, the transfer A to B instruction, and underscore T. Why underscore T? Well, if you just type and, it's like a reserve word, and VHDL does not let you use it. So and type. They do this in C as well, where you see underscore T to denote that it's type. Just pretend it says and. Or has the same issue. Add didn't have that issue. Um, two's complement part one, two's complement part two. It's actually two steps to two's complementing. We have to do two passes of the CPU. We can't do it all in one state. So that's what this is. Shift right logical. Again, reserve word, so type. And out is also a reserve word, so type. If you guys are wondering where these come from, you look at the lab document, load tab and or add two's comp shift and out. It's kind of on the nose when you have an idle state where we're doing nothing. Right? Are you surprised? Hopefully not. And then we have a current state. We always start at idle. This is just the start. This can change. All right. And then we're going to have something really cool from the lab document that saves you like some alt tabbing is you can have these 4 lines. They're constants and they basically just whenever I say this, it means this. Whenever I say this, it means this. You can think anytime you see it, get a little copy paste. It's going to make your life easier. Go ahead and include these. I can't be bothered to type it all out, so I just won't. But boom, right? And hopefully this kind of seems familiar. Like when you wanted to preserve B, you wrote 1, 1. When you wanted to preserve A, you wrote 1, 0. When you wanted to look at the input bus, you selected 0, 0, right? That's all these are. They're just going to be used in our code in certain places. So far we've got inputs, outputs. What did you expect, right? And then turns out we're working with a state machine. Lo and behold, every state machine has states. So we like to name our states. State 1, 0 means nothing to me, but state TAB has some meaning. So, okay. Now, like I said before, process block. Are you really surprised, right? Process, it's going to depend on stuff. It has a begin, it has an end process, right? We're going to depend on like the clock and the reset. Oh, wow, right? Like when something changes, what do we care about? Well, we care about when the clock changes, we care about when reset changes. We don't care about when start changes, right? Because we only care about start at a rising edge, right? Only care state machines only care about stuff at rising edges. Now, if we had like a mealy input or output, yes, but no mealy. No mealy. Okay. Um, no mealy. If we had mealy inputs, yeah, they'd be in the sensitivity list. No mealy. The way the state machine works at a rising edge, we do something. Okay. Someone changes select B, someone changes the input bus. We're not executing the instruction right now. It's not a rising edge. We don't care. Stuff that happens between the rising edges, we don't care about. Okay. So first, I mean, I guess we just say like if reset is 1, right? Then we should probably do something. Doing that something is probably like, I mean, we'll make the state right now equal to idle. What is it like that? Tell me code. Yeah, the arrow points this way. It's gonna equal to idle. We'll make cell A equal to cell A. I'll explain this line in a second. Same with this line. And opcode is going to become this. I think that's all I did in here. So, I mean, reset's got 1, 2, 3, 4. And done, of course, should become true. Cool. So what do these lines mean? Okay, if we reset, we should go back to the idle state. If we were in the middle of executing an instruction and we click reset, yeah, go back to idle. Abort the instruction. We're going to reset the CPU anyways. What are you going to do? And 0 and 0. Shut up. No. Okay. A equals cell A. Maybe you're looking at the cell A and you're like, what is that? So maybe this would make more sense if I did this. Those people confused. Maybe not, right? Remember that I don't have the previous lab open. Yeah, I don't. But we had the muxes, and the muxes would determine what fed the registers. 1 0 means that the mux is going to feed you whatever's in register A. And so if A is feeding A is going to remain the same. So where does 1 0 come from? Well, it's these constants up here, right? So cell A means that at the clock edge, it will keep itself. Cell B means, oops, that at the clock edge, it will keep itself. Now it's itself because B is going to select itself, A is going to select itself. If we wanted them to look at the input bus, we'd use in because that's the variable up here, right? Cool. Opcode being 000, it's a sane default. You know, I could do this. Most of the operations plus 0 are going to be themselves. It doesn't really matter. It's a sane default. And then done being true, of course, if we're in the idle state, we're not doing anything. Okay. Now we'll do a little, see what I did there? Okay. I put an enter here, and we're going to do else, ELS, if, okay? Do not put this below here and then get an error and get confused. That's we're adding an else if to the previous if statement. Okay, so if there was a rising edge on the clock, then we will stuff in here. But first I made an error. Who sees the error? Raise your hand. Leave a comment, like, subscribe, mention me in your gate revals to let me know that you see the error. Um, what about now? Do you guys see the error? What is it? Tell me. You guys know I spent an hour like, why didn't it work? This is the error right here, bro. Look at what it says in my working code that I wrote. If reset equals 0, why would it say that instead of reset equal 1? Reset is active low. Okay, I was running code on this godforsaken DE10, and reset equals 1 means the button's not pressed. So my state machine was constantly being reset every second of every day. Okay. But no, it should be this means reset equals 0. A press is active low. So don't make the same mistake I did. Reset equals 0. Active low buttons. Who would have thought? But not active low switches. Mm-mm. No, that'd be too consistent. We gotta keep everyone on their toes. I'm not bitter. I'm not bitter. I'm very bitter. So yeah, and then I mean, okay. So I mentioned it's a process block and a case statement, but first we're gonna say that CN becomes Cout. Now, hopefully this line makes sense. Uh, they're both bits, but Cout. This guy really should be a standard logic vector. It'll save us time later. 0 down to 0. If you watch my previous video, you know that a standard logic vector 0 down to 0 is really just like it's this or this, right? So why don't we just use 0 or 1, right? What's the difference between these two? And the long story short is that these guys can be used for addition and these guys cannot, right? And so if they're a carry, obviously we're using them for addition. We do A plus B plus carry, right? And so these are more useful. And so we want them to be in that form when performing addition with them. So we receive them in 0 down to 0 form. Sue me. So that's how it is. But now we got to keep in mind that, hey, Cn is a standard logic vector, so we can only address it bit by bit. So you do that. A little annoying. It's the wonders of using VHDL. Deal with it, right? Every time there's a clock edge, we store the previous Cout, and we're going to use it as the next Cn, right? So here's and then here's the clock. Try and do this properly. Ignore this like last part, but okay. So this is the Cout, and this is the clock, and this is going to be the Cn. So if the Cout is low and the clock happens, then the CN is going to be low. But if the C out is high and ignore that line. If the C out is low and a clock happens, the CN is going to be low. But at the next rising edge right here, he's high, so it's going to be high. Okay, and then at the next rising edge, he's high again, so he's going to stay high. But the bit is that the value from the previous rising edge, right? This value right here, right? This my head, so this value right here is preserved all the way up until here, right? And so we can use it again. And so if we just did 2 plus 18 and there's a carry, we can then use that carry again for, 1 plus 2 if we're doing, you know, arithmetic with numbers that are larger than the registers are. For example, 16-bit addition in an 8-bit register. This kind of CN carrying the carry is important. So that's why we're doing this. Every single time there's a rising edge, we carry the carry. Now, recall that the carry is always 0 when we're not adding. So a lot of time, this is just sort of useless computation. If we did A, or A, 1 and 2 or something, the binary for 1 and the binary for 2 ANDed together, the carry out is going to be 0. And then we're remembering this useless 0, but it doesn't take that much energy to run a D flip-flop. And so remembering it all the time is fine. The, the long story short is the CN should reflect the previous cycle's C out. That's what this line does. Okay, now what you guys have all been waiting for, the case statement. Case on state RN is, we got a little end case. Okay, we've got like a when idle. And when, that's not a comment. And when idle. Guess what language I've been writing code in? C++. Boom. And when idle. Okay. Boom, boom, boom. I don't think that there's anything. I'm gonna double check. Start equal. And then an if on the instances. Sure. Okay. So first things first. If we are in idle and start is equal to 1. Right? This is the first thing. And then we have like an else and then an end if. Right? Okay, because we're not going to do anything if start's false. Right? If we're sitting in this idle state up here, right? This guy, and we're not going to go down to and or not or whatever on a rising edge if start isn't true. Start is there so it doesn't just happen willy-nilly. So we can tell it when to do something. Real CPUs don't have the start signal. I think it's there to make your demoing easier, assuming you're using like an actual clock and not a button. But I don't know why you do that when you could just use a button. So it kind of comes off to me as a useless signal, but uh, I'm not volunteering to make the lab. Whoever made this lab, low key, I'm a fan. I don't mind this lab. So don't say I hated when I didn't. So this will be like the next state logic in here. Otherwise, we'll have like some please do nothing. Right? Okay, so what does doing nothing look like? It kind of looks like a reset, honestly. Oh, I just love that it pasted it like that. That's so wonderful. All right, please do nothing. We're just gonna stay in the idle state. We're gonna hold A, we're gonna hold B, we're gonna do nothing with the ALU, and we're gonna have done. Right? That kind of makes sense. And like, that's what I did. I said hold everything instead of please do nothing, but it's the idle state, right? And it's actually not, this isn't a fact about the idle state. This is a fact about being in the idle state with start equals 0, right? If we're not started and we're in the idle state, we're staying in the idle state. And so keep doing idle state things. Next, we have the next state logic. If the instruction is equal to 0, 0, 0, then we should do the 0, 0, 0 instruction, which I'll find in a second. Else, ELS if the instruction is equal to this, then we should do that, right? Okay, and then boom, 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 boom. 1, 2, 3, 4, 5, 6, 7 should be good enough. So binary for 1, binary for 2, 3, 4, 5, 6, and a binary for 7. Right. Okay. And in here, I'll put some comments. According to the lab doc, we've got, oops, here we go. We've got load. We've got tab, which stands for transfer A to B, which is a little bit ironic for reasons we'll get to. We've got and as well as or, as well as add, as well as two comp, choose complement, and then shift right logical out. Okay, so cool, right? Another thing I want to add. Oh, no, I'll add it later after some thorough explanations. But I think that's pretty good. We're probably about halfway done considering I'm going to fill out lab 4 for you guys. And then a lot of these will be left as an exercise to you. And they really just come down to understanding how the part 4 worked. But I'll do two of them. I'll do the hardest one and probably the easiest one. It's probably a good time to compile while I think about it. So I guess one thing we can do that's kind of universal is in the controller. Yeah, I put comments, but we should also probably do a little state rn is going to get load, the load instruction. I'll copy this and it's going to get tab. It's going to get and t. Can't be and, right? It's going to get or t. The way to memorize is if it changes color, add an underscore t. So I write add, doesn't complain at me, no change color. I add two comp to the first part of two's complement. Shift right logical type and out type. This will be like a universal thing for all of them, right? If we go from idle, right, and start is true, so we get down to here. This is like a decision block, right? This isn't a state. It's just which next state should we choose, right? The next state is determined by the instruction, right? So if the instruction is 101, the instruction is 101, we should go to the two's complement. If the instruction is 100, we should go to the add state, right? So these internals still aren't done, and you'll kind of see how and why, but this is definitely a great first step. Now, I have something confusing to talk about. I do. I'm sorry. It's true. Um, it's basically, oops, select. Boop, 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 boop. Okay. The way states work, it's more mealy or something. It's weird. So imagine we're in this state. Okay. This is idle. And we're going to go to the next state, which will be add. Okay. Okay. So in VHDL, you kind of write the code like you're one step behind. Maybe mentally you're one step ahead, but you're one step behind. Okay. Because in VHDL, the fact that we're here, like this line will be run after the rising edge, immediately after, so close after that we know it'll get run right here. You know what I mean? Like very. So what happens in a process block? The rising edge happens. Okay. And the bit is if we have code that depends on a rising edge, we cannot change what happens before that rising edge. Right? So what does this mean? Basically, in this code, we can't like it's hard to explain. You'd think with the ALU and a bunch of other stuff that most of these commands can be executed in one instruction, right? Loading something, that was something you did in one clock cycle. Moving A to B was one clock cycle. Performing an AND was one clock cycle. Oring, adding, this would take multiple. Shifting and moving out. But in VHDL, we can't because we're waiting on a rising edge to perform the action, but we need to know the data at the rising edge. It's a catch-22, right? The instruction comes in at a rising edge, but we need to know the instruction to perform it. Okay. So if 0, 0, if 1, 0, 0 comes in at a rising edge, right? We can't have our cake and eat it too. The rising edge happens, and then we observe 1, 0, 0. Okay. So you'd say, okay, set the ALU up to perform an add. But now we're here, and the ALU only ever adds at the next rising edge, which we'll have access to. We'll be able to write code that performs stuff here in our process block. So it takes 2 clock cycles, and thus we have an idle state and an add state, and we'll have an idle state and a state for each set of instructions because we don't know, right? We don't know when we want to perform instruction, and we don't know what that instruction is. We don't know that until there's a rising edge. Okay. This is very important that you understand this because my design hinges on this, right? Now, you could say, like, okay, we'll just have the falling edge and we'll set up there, but I think that's even more confusing. It would work. It might be faster, but I didn't want to do that. So the TLDR, the main takeaway is that we don't have any information until a rising edge. And once there's been a rising edge, we can't act on it. And so once there's a rising edge, we know what we have to do and we can do it on the next rising edge. But we can't just perform an add in one cycle. We have this cycle right here, this rising edge, which tells us, hey, we're adding. And then this guy, which performs the add. Okay. So, yeah. And so the bit is we're going to set up the add here. This is the setup. And then this is the perform right here. And so remember, I told you that this code is happening right here at this arrow. So we're going to set the add up, or we're going to set the load up. So this is a load. So basically, the first thing we're going to do is we're going to say that done is false. Okay. There's been a rising edge when start is true. Okay. As of right here, as of right here, right? Right after that rising edge, the CPU is working. The controller is working. Okay. We're working from here to here right before. Right. Um, and so the second that there's a rising edge and start is true, and we fall into the load instruction, by definition, we're working on the load instruction. We're not done. Okay. Now, as for loading, we have to read what the load instruction does. It says load dest with in-bus value. Okay, so if the destination is A, remember that was a signal we had, destination is A, and if that is equal to true, then we're going to load, and if, so this will be a load into B, load input into B, load input into A. And this part is the part that is the abstraction. This is the controller doing what we don't want to do for us, the nitty gritty, the under the hood. So we're going to cell A is going to be cell A, which is the same as 1, 0. That makes you happier, but I like the constant. Cell A. Okay. Cell B. What should B point at? Because cell N. Okay. Right. A is getting from the input bus, which would be this, right? So loading the input bus into A means cell A gets cell N, cell B gets cell B, which is the same as 1, 1, but I'm not writing that. Okay. And the opcode, since we don't care, I'm just going to make it 0, 0, 0, 0. This is our sane default thing we default to. Doesn't matter because neither of these are depending on it, so the output of the ALU isn't going to have any bearing on our system. But that's kind of it. Yeah. Now, of course, that was only if our output goes into A. What do we do if our output goes into B? What do we do if our output goes into B? What should happen with A? Well, we should probably hold it. What should happen with B? Well, it should look at the input bus. What should the opcode be? We don't care, so go to the default. Okay? Boom. There's this guy. Okay? Now, remember, I told you that on the rising edge, right, we're going to hit this code. We're going to set up our signals, but nothing's happened. Done's gone false, sure, but nothing else has happened, right? The ALU isn't going to be able to perform with this stuff until the next rising edge. And so at the next rising edge, literally on it, we'll perform this add, and we'll also load the next instruction right here. The next instruction will be in green. And then if there were another like rising edge, it's a really ununiform clock wave that I've drawn here. So say like this. Okay. At that next rising edge, green kind of happens. You can think right before it happens on it, but you can think right before. And then the purple instruction starts right after it, right? So we're kind of doing stuff just before and just after clock edges. It has to do with the fact that at a clock edge, something happens, and then we do something right after. So there's right before and right after. So if we're starting up, maybe there's nothing right here, nothing right here. We have a clock edge, we load an instruction. At the next clock edge, we finally perform it. And then immediately afterwards, we set the next one up. We finally perform it. Immediately afterwards, we set the next one up, right? So it's performing, setting up. Yeah. And so this is the setup. This code with the if, this if statement is this setup right here, right? So how do we execute it? Well, most of the time our instructions are one cycle, and so executing it just means it just means the next clock cycle it'll execute. We've set it up. We just need to hit another rising edge, and then we should go back to idle, right? Typically. So we do that. When, and I'll just say when others, because most of the things will act like this. And it's literally just the same as reset. I'll explain why in a second, but yeah. State RN equal idle. So once we're done with, it says others, but if it confuses you, you can think of it as it just says load for now. But this will encompass everything because I haven't written everything. And it turns out that you should leave it as others except for like one thing, which we'll get to. But I'll get to that when I get to that. For now, this works. It's good enough. Once we're done, we go back to the idle state. We hold A, we hold B, default, and done is true. Okay. So we set up here. A is looking at the input bus. B is going to preserve itself. We execute here. And once we're done executing, we go to the green, which is idle. Okay. Now idle ends, we set up another instruction. So it's kind of a two cycle, two period thing, right? This is what it takes to go from idle to an instruction. And we do that. And now in the red, it would happen again, and we're in idle again. We have to make it to another instruction. Okay. Would it make sense to go straight from one instruction to another? Sort of, I guess. Having idle is really nice though, because we can put all the decoding logic in one place, right? Do you want every single instruction to have next state logic? You want to have this massive if statement 8 times for 8 instructions? No, you want one main instruction that tells you where to do it, and then a bunch of instructions like you want you want this drawing. One deciding many, not like this guy has complex logic that tells you if it has to go here, 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 or eight, real instruction sets have like 800 instructions. This guy's going to point to 800 of them. No, he's going to point back to the beginning. We'll pick one of 800. Back to the beginning, pick one of 800. It's maybe smaller here in a smaller scale. It might be like, why do we have this idle state when we could just go from instruction to instruction? You need it, trust me. And so this is what almost every instruction will do, right? And that's why I say when others. Almost every instruction will just go back to idle and hold once it's done, right? Now, that doesn't mean that every instruction is holding, right? Instructions do stuff with A and B, but after that, they hold. Okay. So, and that's this second rising edge happening right here. Or I guess that's this rising edge right here. This rising edge should be it's technically this. Ignore me. It's chill. One of these will always between this and this, one of them will be the instruction we care about, and one of them will be idle, or they'll both be idle if we're not running nothing. But this guy, when you think about it, was an idle, and this guy is add, and then this guy would be idle, and then the next guy would be add. It's confusing to me, so I try to explain it, but if I'm just explaining extra and you already kind of got it, don't let me trip you up. But anyways, so we've successfully implemented the load instruction. Now we'll also do choose complement, but first we're going to jump over to here. Let's get load working on our board with pin assignments and the like, and then we'll move on to choose complement. So I'm compiling right now, and I'm hoping to see one big error that just says nothing in lab 4. Nothing in lab 4. So let's get to that. Entity lab 4 support and lab 4. Remember, this is lab 5, but and then we've got architecture behavioral of lab 4 is begin and behavioral. Boom, boom, boom. Okay. So, I mean, this guy's gonna need a clock. He's gonna need some inputs or some imports, excuse me. Boom, 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 boom. He's gonna need a reset. He's gonna need a start bit. Um, we're gonna want to output these guys to the thing. So we'll need these guys as outputs. These are the 7 segments, and they represent the state of our RA loop. Input bus, like that. Clock reset start. We're gonna have the instruction. This from memory, guys. We're gonna have the destination is A. Okay. Hmm. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, it's not. I ended up wanting to output done. So I guess we can also output done. Done's going to be an output standard logic. This guy had a lot. This guy is me. Um, 4, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10, 11. And we need the input bus. Yeah. Okay. So the input bus is going to be an in standard logic vector of, hey, 3 down to 0 this time. How cool. Notice that we don't have C in or C out as inputs. Okay. That's because C out is feeding C in. We don't need it. There's no intervention on our part. C in is the last C out, or it starts as 0. Right. Nice and easy. Okay. So we've got this. I don't think I do any like meaningful signals that don't just come up like in an unmotivated manner. Yeah, these are all like low-key very easily motivated. So first thing, we're going to look at our RALU. We're going to think about it. We're going to grab like one of these components. Any of them will do. And we're going to, in our architecture, we got to declare some components. So I'm going to go ahead and do that. Okay, that is absolutely not what I clicked Control C on. Thank you, Cordis. Why don't you just crash and then do nothing? And I forgot to grab the end component. Something like that. Okay. So we need our RALU, right? And so how do you declare components? You go to the entity of the thing you want to import and you grab everything. Notice I did not grab the closing parentheses and semicolon. And then you go to your component and you just paste them in. Okay, that's also just like very clearly not what I clicked Control C on. There we go. There's our component. Hit it with a little tab. Beautiful. We also need a component for the controller. So I'll grab this, paste it, delete the inside, said like delete all of the inside and then like that. And this will be the con. I'll just steal the name because I don't know how to spell it wrong like consistently. I just be typing stuff and messing up in controller. So again, it's the same principle. Just grab the bottom all the way up to the top, omitting this parenthesis and semicolon. Right? Uh, boom, 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 boom. Okay, we've got components. Okay, we've also got some signals, but these will kind of pop out of like a necessity to have them. And then literally all we do in the begin is we instantiate the raw loop, we instantiate the controller, we wire them up, and we're good. Okay. So RALU inst is a RALU, a little port map. And then we just grab all the things RALU has. It has an input bus clock, CN reset, input bus, clock, CN reset. It's got cell A, cell B opcode. Got C out. It's got 7 seg 0 through 3. Something like that. right? Okay, same shit, different day. Got the control control controller inst, something like that, hopefully. Make sure I got that name right. 'Cause maybe I didn't, and we'll just grab this. And the controller it's got a clock, reset. I'm just reading it now. Start, see out, inst, dest is A, cell B. It's got op, which I didn't name opcode because I'm bad with naming conventions, and done. And I just read them like straight from here, straight down to here. Cool. Now we got to actually like perform the wiring. Hopefully, you guys were looking at this like, Joe, what are you doing here? Because you got to do something like this and like some signal here, right? Something like that. So the input bus for the ALU, I mean, it's just right here. So we called it input bus. So the input bus coming from our pin assignment is going to go to this input bus. Same thing with the clock. Okay, for CN, I'm going to make a signal called CN. Signal CN is going to be a standard logic vector 0 down to 0, right? Because that's what the ALU likes. All right, and that's going to be this guy. The reset, we just have a signal for that. It's actually an input cell A. I'm going to make a signal called cell A from the controller. I'm going to say controller cell A. I like that more. And it's a standard logic vector from 1 down to 0. Right? And for now, we'll just stick that on here. Cont cell A. Okay, cool. Now cell B, it's going to get the same treatment. It's except cont cell B. Right? This will be a signal I make eventually, but I just clicked insert. Great job, Joseph. There we go. Cell B, right? Cell B, cell B. This will be a signal, and then the opcode is going to get cont opcode. That's again going to be a signal I make. Remember, working on the ALU here. The C out, that guy's going to be a C out, which is a signal I'll make. And then SSG0, this is a signal all the way up top. SSG0, right? So we'll just all the way to SSG0. 1, 2, 3. Okay. Now there's some signals I didn't make there, so let's make those. We got a signal for cell A, we got a signal for cell B, got a cont opcode, which I believe is 3 bits instead of 2. We got a signal for the C out, which is just a standard logic. Okay. And if you're wondering when and why you should make a signal versus not, anytime I didn't make a signal, the thing I wanted was up here. Signals exist to map things between components. So when I look in the lab document and I see cell 1 and cell 2 in an arrow, I see C in an arrow, I see op in an arrow. That's 1, 2, 3, 4 signals. Okay. 1, 2, 3, 4 signals. Okay, so where's the fifth one coming from? This arrow is really, if I had it here, but I didn't. So I'll get it there as quickly as I want. Boom, 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 boom. This arrow is really an arrow from here to here, right? Like this. So there's 1, 2, 3, 4, 5 signals. You may be like, why aren't these guys signals? Because they're coming from pin assignments. Why isn't this guy signal? Because it's coming from pin assignments. So that's kind of how I see what's a signal and what isn't. And also just kind of the intuition that it's going from component to component, it must be a signal. So those are the signals. Pretty sure I did all that right. So now we're going to do the controller. Much of the same, like we already have a clock, so just type it in. We already have a reset, so just type it in. Start signal is going to come from pin assignments way up here. So we just have it. The C out is a signal I already defined, so I'll just stick that there. And that's what I mentioned. The nomenclature is really nice and easy. C out goes to C out. Cn goes to Cn. Okay. Name it such that it's like that, nice and easy. Okay, inst, I called it probably something different up top because I'm stupid. And I called it inst, so we're good. Coming from pin assignments, dest is A. It's coming from pin assignments, dest is A. Cool. Okay, cell A. This is going to be from our controller, cell A, right? That's this wire here. Same thing, cell B. Hey, that's the controller cell B. Opcode. Oops. Hey, that's the controller opcode. Cn goes to Cn. That's a signal we already defined. And done, gonna go to done. And that's a signal way up top. I'm not gonna scroll. But the kind of cool thing about signals, if you've been seeing this, it's been confusing you all semester, what I'll try and describe is that if you put a signal on one output and another input, it joins them, right? So um, cell A for the controller is an output, okay? And the other place we use const cell A is here. Cell A on the RALU is an input, right? So if it's tied to an output on one end and an input on the other, that's what we want, right? If it's tied to two inputs, that's bad. Which one should we use? If it's tied to two outputs, that's bad. Which one should it have? So you tie signals to an output on one end and an input on the other, and it acts kind of like a wire between those two things. They're great. So we'll compile this. I'm sure I made an error somewhere. We'll program it on our board. We'll watch our first command run, make two's complement, and then you guys got the rest from there. I have faith in you guys, especially because the rest of them are very easy, assuming you've got the first two. There we go. So I'll program it on the board. Psych. That's what I would say. But we got to do assignments pin planner. Now, ideally, you know how to do these, but I'm gonna do this tutorial with the assumption that you had the pin assignments from Lab 4 already. If you don't, you're cooked. A few things. First, why is dest is a like, did I name it differently? Did I name it differently? I called it dest. Yes, so that's why. Anyways, assignments, pin planner, it's already open. Basically, you're going to leave clock alone. The following is assuming that you have your pin assignments from Lab 4 set up properly. If you don't, just set them up, right? There's nothing for you to try and preserve. Keep clock, okay? And everything else, we're going to either keep it or delete it, and then we'll recompile and they'll show back up. So dest is A, is new, delete it. Done is new, delete it. Yes, input bus, delete. What does it say? Can't delete bus bit. I mean, I'm pretty sure you can, Quartus. I own the computer actually. So you can't delete it. So the next best thing I can do is delete the pin assignments for you guys. Bop. Yeah, sure. Bop, bop. Okay, so leave clock the same. Do you typically delete these and they disappear? But I guess it's fine. Inst. You guys wouldn't have this, so there we go. Reset, you guys would have. Keep it the same. Okay, this is what's really nice. All of these assignments, 7 segments, 0 through 3, they're all good. Leave them. They're the same. If you're really curious, where do I find them? Go to the mill website, DE10 pinouts, scroll down. It's this table. Map the segment 0 to its segments. But if you already did this for lab 4, no need to repeat it. Right? Okay, start is this guy. We're going to delete start, and dest is new, so we're going to delete him. So the only pin assignments we kept were clock, reset. I don't know where reset went, which is kind of frustrating. Oh, here he is. Clock, reset, and the 7 segment outputs. That's what we kept. Again, the only things we kept, clock, reset, and the 7 segment outputs. We'll be showing you guys how to do the rest of those pin assignments. We close the pin planner. Let me compile again, and then I'll reopen it. Yeah. So a lot of the stuff you actually will have to click delete on. Like if you had some signal called cell A and it's no longer being used, delete it. Right? I deleted the assignments, but you should delete the old pin names, right? If I have something in here called stupid, it's an in standard logic, and I compile with it, it's going to show up in Pin Planner. Even if I do this, it will still show up in Pin Planner. And so you should manually go in and delete it. You only want these signals. Anyways, I'm getting sick because I'm working too much. I can feel it. So now we'll get on to these. So the input bus. The input bus should be these switches, which are the switches closest to here. This is switch 0 and this is switch 9 all the way to the end. So we want 9, 8, 7, and 6. So we go to our trusty table. 9, 8, 7, and 6. That's F15. Okay. On the most significant, it's F15. B14, A14. A14, A13. Cool. Okay, the instructions, those are going to go on these switches right here, 0, 1, and 2. So instruction 2 will go on switch 2. So D12, C11, C10. Okay, the dest is A is going to go on, this was 0, 1, 2. It's going to go on 3. So that's C12. And then done, remember I was showing done on this, the middle of this LED indicator here. So we're going to stick done on N20, I believe. Maybe it was M20. On N20, this guy. This is the middle of the last 7-segment display. So it can be a little guy in the middle. N20. Finally, the start. He'll just go on the next available switch. We've used these 3 switches for instructions. We've used this switch to talk about the destination. So we're going to use switch 4, which is A12 for the start bit. And then we use these last 4. Remember, we used up to switch 4 for that stuff. And then we use 1, 2, 3, 4 for the input bus. We have a switch left over. Cool. Super cool. Awesome. Right. So we went from not enough switches to too many. So that's kind of the power of the controller. And hopefully you'll find using it and demoing it a little more intuitive than before. Anyways, now the pin assignments are done. We're gonna compile. And I low-key have some stuff due at like midnight. It's 11:17. Might be doing that stuff late. So you guys are welcome. I'm gonna plug my DE10 in. Boom. We're gonna wait for this to compile. All that's left, if this works, little demo to show you what's happening. We'll make two's complement, and the rest is up to you guys. Hint, just go into the thing, right? Transfer A to B or transfer B to A, really, depending on the dest, and just have an if statement, right? If it depends, like if you go into here and you look at the table, sometimes it'll tell you like dest equals dest equals dest equals dest 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 dest. All of these depend on dest. So all of them will have this if statement. If the destination is A, then you perform it with A as the destination. If the destination is B, then you perform it with B as the destination. Right? All the other instructions are one cycle. You put the if statement, copy this if statement, and then change cell A, cell B, and opcode. Change cell A, cell B, and then opcode accordingly. Right? Also make sure to have done. The basic template for these, leave the state RN thing, add that done is going to become false, right? Add the if statement, add this if statement, add an else statement, add an end if, and then here you do your thing with B as dest, and then here you do your thing with A as dest, right? And that's except for two's comp, which we're going to go over together, this is the pattern you follow, right? So anyways, we've compiled. I changed it so it's like not happy about it, but I don't care. Load, it says it failed. I own you. Click it, load again. Says it worked. I'm gonna look at it with my own eyes first. Seems to work, seems to work. Let's try and load 1 into cool. Cool. It's working. Okay. So if you followed up to this part and you did everything right, boom. Input bus. Input bus is over here. Input bus should be working. 8. There's C. Here's 1, 5. Okay, little, this is A, this is B, this is the ALU output, this is the input bus. So let's stick something on the input bus. Okay. 0, 0, 0 is the instruction we loaded. I'm going to do down, 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 down. Everything's down except for the input bus. Click the buttons. Nothing happens. That's because start is not true. We make start true. That's this switch. 3 for instruction, 1 for destination, 1 for start, right? Now that start's true. We click once. Nothing happens, but we see the I'm working light come on. This means done is now false. So the instruction is being run. Okay. Now we click again and you see it loaded and done went back. Now nothing's happening because we're loading 8 into the same thing. Okay, let's try and load something else. Let's put 5. That's 2, my bad. And now we're going to change the destination. Same instruction because you only ever implemented one instruction. That's 0, 0, 0. Now we're going to change the destination from A to B, or actually from B to A, right? This is B, this is A. 0 is B, 1 is A for me. So again, we press it. We see that it started the instruction, but nothing happened. We see that the instruction was executed, and now done is true. Busy is false, right? The reset button works. Yeah. So typically, most instructions, you're going to click the button. Nothing's going to happen, but you're going to see this light come on. You're going to click the button again, and the light's going to turn off, and the instruction will execute. For two's comp, it's a little different, but you know. Um, Reset. One other thing you can try is like load something into the input bus, make start false. Press the button as much as you want. Nothing's going to happen because start is false, right? So that's what we did. Okay. Sorry, I just unplugged my computer. It's a garbage computer that no one should have to use, but I use it. It lagged when I unplugged it, which made me upset. Anyways, let's implement two's complement. How do we take the two's complement of a number? I wonder. How do we take the two's complement of a number? I don't know. I don't know. So you take the number, you flip all the bits, you add 1, and this will lead you to the two's complement representation of that number. Cool. In ALU terms, what does that mean? We performed a complement and we performed an add. Two things. Two things means two states. Right? Okay, so we can at least do the first state and it should be relatively easy. So we go to the two's complement block right here. And first thing we do is we say, hey, done. That's going to get equaled to 0. Now keep in mind something, and this will make testing very confusing, but it's fine. Destination gets the negation of reg A. We always take the two's complement of reg A. If you're loading something into reg B and then running the two's complement, it's going to look like it's broken because it's just taking the two's complement of 0 because you didn't load anything in reg A. You just loaded something into reg B and then you tried to run it, but you thought you loaded something and then took the two's complement of it, but you loaded something into B and then took the two's complement of A, right? You can only ever take the two's complement of register A. Get that in your head. Okay. When you're testing it, which I did a lot and was convinced it was broken for a very long time, you need to know you can only take the two's complement of something in register A. Now it can go wherever, yes, but it's good to know. Anyways, what was I saying? Anyways, so the first step, done equals 0. And I believe we don't even need an if statement for this, but I want to double check because I don't want to lead you guys astray. Yeah, we don't. Okay. So done is 0. The next state is this. Okay, now for two's comp, we take the one's comp or negation of A, and we load 1 into B. Now, how are we going to get 1 into B? We're going to use the input bus. Running two's complement requires that you stick a 1 on the input bus. There's a different way to do it. I'll go over it. It's needlessly complicated and out of the scope of this class, so we're going to do this way. So first, how do we do the one's comp of A? Well, cell A is going to end up being cell out, right? A is going to become the output bus, And that output bus is going to be whatever code it needs for us to do a little negation. So what is that? I don't know. Go into here, go into RaLU or whatever you called it, and go look at your ALU. Look at your ALU and look for this line where you do the negation. What code is that? Well, it's 000. Okay, cool. So go back into your controller. The opcode we want is 000. So what is this saying? This is saying prepare during the next rising edge. During the next rising edge, our state will be the first part. This one means first part of 2's complement. We're not done. We're going to perform the negation of A and stick it into A. Okay, cool. What was the other thing I mentioned doing? Loading 1 into B. Okay, so cell B is going to load cell input bus. All right. So we can do all that in one clock cycle. And the next clock cycle, we'll be performing an addition. Okay, cool. So that's that. Now we go here and we say when 2's complement part 1, and then we'll have a little end to comp2_1. So when we're running this code here, this means, I wish I had my old drawing. This means, hey, we had a rising edge. We set up the negation of A and the loading of 1. Okay. The rising edge happens here. We just performed that. And now we're in this green spot. We need to set up the second part of 2's complement. We'll be able to perform that here and also go back to idle. Okay. So we need to perform the second part of 2's comp, which is just add A and B into dest. Cool. So we have the same if statement that you're going to have in like every single instruction, which makes me think there might be a better way to do it, but I can't be bothered. Repeating code typically means you're doing something very stupid, right? So we've got this if statement, and basically we need to add A and B into A plus B into A plus B into B. And you might be like, well, what about the carry, right? This is the ALU always uses CN, right? What about the carry? We know that the CN will be 0 because we know that if we're in the state, the last state was this 2's complement part 1 that we just ran. And we know that that instruction is a negation, and the C out of the ALU for negation is always 0, so like we don't have to worry about it. Anyways, A plus B into A. Okay. So A is going to be looking at the output bus. B is going to be holding its value. Because like what else should it do, right? It makes sense to have it hold its value. And the opcode is going to be whatever the opcode for addition is. And again, I don't memorize these things. Go to your code, go to the ALU, look for the addition, look something like this, and the code was 011. Cool. Oops, that means highlight everything. And then what do we do if we want to stick A plus B into B? This is something you guys have to know the difference between because it's the 6 other commands. Well, A is going to maintain itself. B is going to look at the output bus. See how the things changed? It's just what's holding versus what's looking at the output. And the opcode is the same because we're still performing an addition. Okay. And the next state, few things we gotta note is that hey done is still gonna be false, and that the next state is gonna become like 2's complement part 2. Okay. Which then hits others, which takes it back to idle. Okay, so 2's complement. It's a longer instruction. So first, we're in idle. We're in idle right here. Okay. We're in idle right here. We hit this. Nothing happens, but we set up. We set up so that we load from the input bus so that we negate A. Okay. And busy goes false. So the light turns on that says, hey, I'm working. Okay. This rising edge happens. We perform the negation. Okay. We load 1 into B. And then we're in part 2. We have to wait. The next rising edge, we perform part 2. Okay. And then this one, we're back at idle. So this guy took typical instructions will take like this long. This guy took this long. Okay. And then we're ready to execute more stuff here. So typically instructions like this isn't like this design comes from the fact that we're designing a very simple CPU. Real instructions don't like take a variable number of states, right? Real architectures that would be so stupid. I think the longest, in fact, I know real processors for one they have pipelining, and the instructions are dictated by the length of the longest instruction. So if I don't know, reading something from memory and then raising it to the power e and then taking the ln of it and then dividing by 8 happens to be an instruction. In assembly, there are some pretty convoluted instructions. Um, Probably one of the more convoluted ones that's very common is increment and decrement. You have to load something with the number 1 or 0, or you have to have special hardware, or maybe you have a floating point operation instruction. What I'm saying is certain instructions are going to be way longer than others because they're just more complicated. And the longest instruction dictates all instruction time. Now, for this lab, no, right? Some instructions take this long, some take this long, right? You see what I'm saying? Some take 2 periods, some take 3. Some takes 1 state, some takes 2, plus the decode IO state or whatever you want to call it. Um, just like don't go into industry or the real world thinking this is how processors work. I think designing it like this is good because it kind of shows you how they could work and it gives you a very deep, low level understanding of a way you could do it and thus a way they work. Even though it's kind of wrong, it's not how people do it. This does really convey what's happening under the hood. We're decoding, performing. Maybe we need to perform multiple steps. So hopefully this makes sense because it's low key important. But the big thing I want to stress again is that your code is running here, right after the rising edge. So basically, we're doing 2 things on a rising edge. I'm really trying to drive this home, explain it as many different ways. We perform what we set up before, and then we set up again. Okay, 2 things on the rising edge. Okay, so when we hit this line right here, we're in this. The fact that we hit this line means a rising edge happened. We performed the first part of two's complement, and we're setting up the second part. Okay, then we're going to perform the second part and set up idle. Okay, let me move. Okay, there we go. And then we're going to set up idle and listen for the next instruction. Right, so that's cool. And I believe we're done. I'm going to compile this. Hopefully, we get no errors. And this has been a great intro to Lab 5, hopefully. I saw Omar made a reply to my video. I should have shouted him out at the beginning. He said, Lab 5, you're not cooked. Listen, Omar, he has no idea how cooked I am. It's not funny. If you guys knew how cooked I was, if I could beam my thoughts into your brain, what you do, can't say it on YouTube. Can't say it. You'd be super sad. That's right. How have they not graded the circuits exam, by the way? Are any of you guys watching this in circuits? I need to know how I did. What if I like failed? 6 days to break. It's actually 5 days and 28 minutes. I don't think I can get the rest of my homework done in 28 minutes. So I think I'm just gonna call that assignment late. But it programs, we already set our pin assignments up because we're goaded. We're gonna hit a little start. It's gonna say it failed. Not. Okay. I'm gonna do some like testing where I make sure it works without showing it to you, and then I'm gonna show it to you, and then you guys are gonna do the rest of the lab on your own. Good luck. Like, what's the two's complement of like 4? Okay. So 1011 is B. Okay. And B plus 1 is C. Okay. And now let's perform the two's complement of C. 1100 becomes 11, so it should be 4. It's kind of obvious. Yeah, okay, cool. And if we're done, we can like go back to here and load like 1. Awesome. Okay, yeah, this works. I'm really proud of the fact this worked first try. Just so you guys know, I pressed the reset button. Good job, Joseph. I have to reprogram my D10 now. I think I just shorted two pins with my sweat and it broke. It's fine. I have it back. You guys don't got to worry about that. Okay, I'm going to show you what to do, what not to do, and we're going to be done. Okay. First, look at this. Input bus working as before. We're going to take the two's complement of the number 4. Okay. So first, let's load the number 4 into A. So 000 is the load instruction. Um, this guy right here is the hey, destination's A. So we're going to start. Oh no, nothing happens. That's because we need to put the start on. Okay. So now that was the first state. We loaded it. Okay. Now we're going to perform two's complement. I'm going to put everything back to 0 and we're going to walk through how to do that. First, whenever you're performing two's complement, you must, yes, must put a 1 in the input bus. There's a different way to do it. I'll explain at the end if you're interested, but two's complement requires a 1 in the input bus because we need to load a 1 into B and like that's the easiest way to do it. Okay, we put a 1 in the input bus. Next, the code for two's complement is 1, 0, 1. Okay, I happen to want the output of this two's complement to go into A because I'm going to end up taking the two's complement of my result to make sure that they're equivalent. So 1, 0, 1, that's the two's complement instruction. Okay, 1, that's the start signal. 1, 0, 1, destination's A, start signal. This guy's an unused switch. Okay, so we're going to go. Okay, first instruction. You'll notice nothing happens, but now we're busy. Okay. Next, we're gonna negate 4, stick it in A, load 1 into B. Okay, the negation of 4, the negation of 0, 1, 0, 0 is 1, 0, 1, 1, which is B. So we should see B, the ones complement of 4, load into A, and we should see the number 1 from the input bus load into B. Boom, that's exactly what happened. Notice we're still busy even though we pressed the button twice. That's because this instruction is longer. Now, next part of two's complement is adding. We have to add B. We have to add A and B. Take the ones complement, add 1. So this is the ones complement. This is 1. You'll notice the ALU already has the output for us. We're going to put this result into A. 1 plus B should be C. And busy should go false. Exactly as expected, okay? Now I'm going to go through that a little faster. We're going to take the ones complement of C. Okay, boom. First, we started the instruction. Nothing's happened. But we're going to take the ones complement of C and we're going to load 1 into here. 1's already in here, so it won't look like anything changed. One's complement of C happens to be 3. 1, 1, 0, 0 goes to 0, 0, 1, 1. Awesome. Now we're going to add these two. Should be 4. And so it makes sense. The two's complement of 4C and the two's complement of C is 4. That's kind of definition of two's complement, how it should work. A few other things to note. As long as this light is off, we have the freedom of picking an instruction. Okay. So this light is off. We're not busy. You can pick an instruction. Let's load 2 into B. 1, 2. It did it. Okay. Let's load 2 into B, but in the middle of an instruction. Okay. So let's load 2 into B, and then I go and I change like the start bit. 1, 2, 3, 4, start bit. Okay, that was a poor example. Let me reset. Okay. Let's load 2 into B. This 0, 0, 0 is the load. The destination's B. We have the start bit. Boom. We started it. Now I'm going to take the start bit and I'm going to flip it low. Okay. Is it going to execute or not? The answer is yes. We started the instruction. There's no stopping now. Only thing you can do is press reset. That's the best bet. Okay. So the start bit's only important when this guy is off. When this guy's on, there's no unstart. There's a reset, of course. There's no unstart. Now, what can change is halfway through an instruction, you can change stuff and it'll actually have an effect. What do I mean by that? Let's load into A with the start bit. We have 4. Okay. So we're going to load 4 into A. Boom. Okay, now I'm going to change the input bus. We're like partway through, but nothing's changed. Change the input bus to be like 6. You'll see 6 goes into A. We look at the input bus, boom, right? So the input bus can change during an instruction. But the only thing that we're ignoring is start, really, and the opcode, right? If I'm in the middle of two's complementing 0, zero's two's complement should be 0, by the way. So we're going to two's complement into A, 1, 0, 1. Okay. Okay, we're starting two's complement, and then I go back to loading, and I turn the start bit off, but I keep the cell A. Okay. There's no stopping it. There's no stopping it. Let me make sure that did what I thought it did. Oh, it didn't work because I didn't have 1 loaded in the input bus. Let me double check that. Hmm. There we go. Okay, yeah, sorry. Load one in the input bus. I didn't have one load in the input bus, so choose comp wouldn't work. Or I was confusing myself, but let's say we're gonna choose comp. Um, boom. Okay. And then I change it, and then A is 9, so the negation of 9 is 6. Yep. So 7 into B. Yeah. So it worked. It works. You can't like once this light goes on, there's not a lot you can do. Once this light goes on, I'm not looking at the opcode, right? We're already executing the structure. What do you want me to do? Go stop what I'm doing, go to another one? We're not looking at the start bit. We are looking at dest and we are looking at the input bus because those just get read whenever they get read. And so if you change them halfway through, that's what's going to happen. It's not going to break anything. It's just going to mean that if you loaded 4 and then you change it to 3, now you're loading 3. Right? So, yeah, hopefully you guys found this helpful. Um, yeah, I think this was a great stepping off starting point for Lab 5. Um, hopefully this kind of made starting a little less daunting. Hopefully you guys understand how to implement the remaining instructions. And yeah, have a great Thanksgiving break in 5 days and 20 minutes for me. It'll be midnight and I should be in sleep, but I'm not. Thank you for watching.